So let's talk a little bit about the end of the semester here, which is surprisingly quickly approaching. Hi, Miss Garcia. Who are we looking for?
Ben Keenan.
Thank you.
It's not usually the response I get.
So we end of semester rather quickly approaching. This is my tentative plan for the end of the semester. Notice here that for this test 4, we're going to try to do that still. I want to do it as an open homework test. So anything that you've written as a homework assignment that you've written by hand, you can use on your test. Chanel?
Could we, are we allowed to copy your notes from OneNote and use that, or no? Can we do homework?
Only homework.
Okay.
Should be in your own pen. If you are a not usually write things out on paper, if you're a write it in OneNote person, that's fine, but you'll need to make sure that you've printed your OneNote pages, and you'll want to make sure as you're writing them that they're something that'll print, like they're in a form that'll print well, that you don't have like writing across and it's like printing on 3 pages this way or something. Like you'll want to check yourself there a little bit. But anything that you've handwritten as homework, you can bring and use. Now, I'd be careful about this because you don't want to end up with like 2 inches of paper that you're trying to sort through looking for things. Like that's not going to be very effective. I probably wouldn't bring all of my homework, but rather just highlight the things that are like, this was a tricky dog. I want to make sure I have an example or 2 doing this kind of thing, or like, and some of the other stuff that's like, yeah, that was easy, that was trivial, like I'm good, I can just study this parts and be good. And then, because I would not want to be overwhelmed and spend 20 of my minutes just leafing through homework assignments trying to find the stuff that I was looking for. So that being said, leading up to this open homework test, we're not going to do any homework quizzes. Because you're a fool if you're not doing your homework assignment if we're going to have an open homework test, right? Like I don't need to check you on doing this now and create a further incentive to do this. We're just going to free up some class time by not using that to do these homework quizzes to get to this test. Chanel?
Are we allowed to, are you going to put AP classroom problems? Are we allowed to print those out and solve them and bring them?
Sure.
Okay.
Yep. And I will eventually get to that. I just haven't gotten there yet.
It's okay. No, I was just curious.
Yeah. Okay. So we'll still be working a little bit on 3.9. I want to devote a little bit of time today and a little bit of time on the next class to still kind of going back and taking some questions from 3.9 and doing some more examples of these kinds of things. Because I think they're important, and it's not, it's not easy to get all at once, and sometimes it takes a little bit of practice and circle back, and a little bit more practice and circle back before things start clicking into place. If you did the 3.9 questions for my AP on the asynchronous day, which I hoped you would have, the beginning, the questions should have felt pretty okay. The first half-ish should have felt reasonably comfortable, and by the end they are quite difficult. And that should have been how that's how that should feel for you. You're right on track if you're like, yeah, the first half or third or so of the questions felt pretty doable. Felt like I was doing what I was, like I was getting things right and things were working out and it was under control. And it started kind of getting progressively more difficult as I went through. They were organized that way so that the real, the bears were at the end and the softballs are in the beginning. But if you're able to, if at the beginning you're already in trouble, you'll want to make sure you come see me for some extra help, or you get going on that a little bit and make sure that you kind of catch back up, because the first half or so of that should have felt pretty doable. Is that okay? So today, I'd like to start with just taking some of the questions from the book problems for 3.9. Tomorrow we'll take some of the MyP 3.9 questions if you want to do some of those. Chanel?
26, I think it was the one with the swimming pool.
Okay, let's take a look. Oops, okay, yeah, so that's... Did you guys notice that on the digital version, that one page was broken? Page 249 or whatever, the page with half the homework assignment, at least it was broken on mine. This page. All right. So 26. Oh, sure. A swimming pool is 20 feet wide, 40 feet long, 3 feet deep at the shallow end, and 9 feet deep at its deepest point. A cross section is shown in the figure. If the pool is being filled at a rate of 0.8 cubic feet per minute, how fast is the water level rising when the depth of the deepest point is 5 feet? So let's start by, I would say drawing a picture, but we kind of have one already, right? Is that, so far everybody's okay with that? Okay. So let's think here. We have 20 feet wide, and I'm going to put a subscript on all this stuff. P for pool. 40 feet long. And then the depth of the pool in the shallow end is 3. The depth of the pool in the deep end is 9. And we know dV dt for the pool is, oh, that's not for the pool though, that's for the water. Right, because we're putting water into this. Come on, you stupid thing. dV dt, water. And we want d h. Well, let's call it depth, right? dt, when the depth of the water is 5 feet. And that's what we're looking for. Everybody's okay with this? If I were to think about this a three-dimensional shape, what type of figure is this? If this is the cross section. Well, it's a prism, right? Because the faces of that figure are going to be rectangular, right? That's like one end of the base is the picture we have given to us, right? Each base is that same picture that we're given to us, and then there's like, so that to me looks like that's got to be the width of that thing, right? 6, that's 18, and then 22, so that's the 40 in the picture. So the volume for a prism is area of the base times the height, right? So the volume for our pool is going to be the area for the base of the pool times the length of the pool, or I'm sorry, the width of the pool is what we call that part. So far, so good. Now that width of the pool, or even when it's filled with water, the width of the water, that'll be a constant, right? It's going to stay 20 feet long, regardless of whether you put water in it or not, right? So that part's a constant. Now, let's talk about how to calculate the area of this thing. So how would we do that? Well, I would break it up into a rectangle here, right? So that's 3 by 40. And then a triangle. So that triangle has a base of 6 and a height of 6. And then I have that rectangle, which has a base of 12 and a height of 6. And then this other triangle, which has a base of 16 and a height of 6.
I didn't understand. Where'd you get the 16 from? It's because it lines up. The base lines up with 16.
Yeah, right? That's all. Is that okay? All right, and that's a big number. What is that? That's 120 plus 9 plus 72 plus 48. That's not a 9, it's an 18, dum-dum. Yeah, thank you. All right, so 18 and 72 is 90, so that's 210. So 258. That look right arithmetic wise? The problem is that the water is going to be variable, right? At least to some extent. So like if I have water like in there. So let's see if we can rewrite this as some pieces here. So we're going to have like, those are all, we called those lengths. So this is going to be like L1, or I'm sorry, that's a depth. Depth of the upper times, well that, hold on a second. Oh, at the depth of 5 feet. Okay. So we're never going to get to that upper section, so I don't even have to worry about it, right? Okay. So let's do that. Base for the water. So I don't have to worry about that section. And then it's going to be L1 well, 1/2 L1 times depth 1. Well, actually, depth is just going to be constant. Yeah. And the next section is just going to be, well, that 12 is a constant, right? And then the third section will be 1/2 L2 times depth. Everybody's okay there?
Wait, how'd you get the value? Sorry, the L1 times D.
Well, that's like L1 is there, L2 is there. That's just like the depth of the water.
So why'd you, to get the area upper?
And now if I look at what I'm looking for, I want just the depth of the water, right? So I want to find a way to rewrite this L1 and L2 in terms of just the depth of the water. So if I look at what we have there, so I have, let's see, 6, and then 6. So that's my tank. And then that was L1, and that's D. So I can write or those are similar triangles. So we can see that L1 is just the same as D. If I do the other piece now, it's 16 and 6. So what can I say there? I can say 16 over 6 equals L2 over D. So 16D is equal to 6L2, or 8 over 3D is equal to L2. So now I can say the volume of the water is going to be 1/2 dW squared plus 12 dW plus 4/3 dW. Oh, squared though, right? Times 20. If I do the derivative of both sides, that's going to be dW dt plus 12 dW dt plus 8/3 dW dt times 20. We know that this is 0.8, and we know that dW is 5. And now it's just solving, I think. So we got here 17 plus 40/3. 17 times 3 is 51 plus 40, so that's like 91/3 dW dt. And we'll just divide that 20 over. Maybe we'll think about that as 4/5. So we're going to divide that 20 over, that's 4/5. That's like 1/25. And then, so we have 3 over 25 times 91 dw dt. Let's see. I don't know. Should have probably looked at it before. 4/5 times 1/20. Let's see. They wrote it as over 2275. That could be what that is. $2,275. Good. Okay, so I did do that right. Yay! Questions? Where'd I lose you? Okay. Where do we need to backtrack to? Very beginning and walk through it again?
I don't know.
Just
I'm gonna start with that.
okay. Let me be honest here. Giselle, if you're confused, everyone else is confused. Okay? So it's okay. Let's go back and just start at the beginning and talk through it again, okay? Because this was a hard one. This is one of the harder ones on here. This might have been the worst one. All right. So I started by just writing down the givens, right? So I was given some dimensions for the pool. I noted that this was a constant, because that's like, you know, like this side of my prism or whatever. This is a hard picture to draw in 3 dimensions. Maybe we think about it, get all that stuff out of here. It's like, you know, it's like, that's that side, right? Can you see it in your head? Okay. So I noted that was a constant, and then I said, okay, what are we looking for? It's looking for the rate in which the water level is rising. So the depth of the water, the rate that's changing with time. So dw dt, and I put the w in there just to not confuse myself between what's a pool dimension and what's a water dimension, right? Because the pool, or the water, is filling the pool, right? So it's taking whatever shape the pool is. So it'll be the same shape as the pool. It'll just be different dimensions, right? But it'll be the same shape figure. So I said, okay, well, volume is changing with respect to time, so it stands to reason this is probably a volume equation that I need to write. The shape of this pool, the 3-dimensional shape that this pool is a prism, because I have like some polygon on one end, polygon on the other, and the faces are all going to be rectangles when I connect lines to the 2 bases, right? So that's a prism. The volume formula for any prism is area of the base times the height or in this case, how long the pool is. We called it length in our problem. Oops, except I meant width. That's what I meant. Sorry about that. That would have been confusing. The width is the constant, because this is the 40 here, and that's the 9 there. So what I started by doing is saying, okay, well, the area of the base is not going to be trivial to calculate because look at the shape of that base. Like that's cuckoo looking. So I said, okay, let me just calculate the area of the base of the pool with numbers in it so I can think about like, what do I really need to do? So I said, okay, I'm going to break this up into like 4 pieces. So I'm going to break it up into those 4 chunks to calculate the area. That feel okay? So for chunk 1, that's just 3 times 40. Chunk 2, 1/2, because it's a triangle, and then 6 times 6. Chunk 3, just 12 times 6, because it's a rectangle, and then 1/2, 16 times 6, because that's another triangle. Is that okay? Okay. So then what I looked at, okay, so that's how I would calculate the area for the pool. So what about water? Because that water is at like the height and widths of these things are going to be different depending on how high the water is, right? So I then went ahead and said, okay, well, the depth of the water we're looking at is 5 feet. So that shallow end up here doesn't even matter, right? Because the water is going to be under that anyway, so I don't have to worry about that. And then I said, okay, well, I'm going to call that length 1, and I'm going to call this the depth of the water. Come on, I wanted a subscript on there, fine. This piece, the 12 is constant, right? Even as I add water in there, doesn't matter what the depth of the water is, that 12 is constant. Okay. And then this next piece, I'm going to call that piece L2, but the depth there is still just the depth of the water. So that gives me this equation for the area of the base. Now let's put some W's on those. Does that feel okay so far? Now the problem is if I go and I try to differentiate here, I'm going to get a dL1 dt and a dL2 dt when I do my differentiation. I don't have any information about what those rates are. I have no way to gather information on what those rates would be. So I know that I'm going to have to find a way to get rid of the L1 and L2 out of this equation and rewrite those parts, the L1 and L2, just in terms of depth of the water. Because that's the derivative I'm looking for, is the dw dt. So I need to take a pause here and let us catch up. Are we doing okay? Okay. So what I did is I took this end and redrew just that part of the picture. So the black is like the pool dimension, and the blue is like our water dimension. And what I noticed here is that those two things form similar triangles, right? Because they have one included angle, and then the L1 is parallel to the 6, and the L2 is parallel to the 16, right? So that's going to give me the similar triangles. So because they're similar triangles, I went ahead and wrote the proportion. So I said like 6/6 is similar to or proportional to L1/D. Now 6/6 is just 1. So if L1/D is equal to 1, just L1 and D have to be the same, right? Because they can't be negative, because they're dimensions. And I'll do the same thing over here. 16/6 is going to be L2/D. And maybe we should have said, DWs or whatever. So again, I just cross-multiplied and simplified and got that L2 is 8/3 DW. Yes?
Can you just explain what the L1 and L2 are? Like, is that just the depth of where it's rising?
That's like the width of the water. So like, Giselle, what we're trying to do is write an expression for the area of the base for the water. Now at every different depth, like the base of those triangles is going to be a different length, right? So that's what L1 represents, is the base of the triangle formed by the water right there. And L2 is like the base of the triangle formed by the water on that side, or that end. Is that?
Yeah.
Okay. So I went ahead and plugged those in for L1 and L2 to get this equation. That's the equation for the base of my water. So I'm going to take that now and plug it into my volume equation. And then differentiate. So when I take the derivative of volume, I get dv dt. When I take the derivative of 1/2 dw squared, I get 1/2 times 2 dw, or just dw, times dw dt. When I do the derivative of 12 dw, I just get 12 times 1 times dw dt. When I do the derivative of 4/3 dw squared, I get 4/3 times 2 times dw times dw dt. Gosh, I should have probably said this should be like dd dw. And that's all still times 20 on the outside. And at this point, now I'm just plugging in. So I knew from before that dv dt was 0.8 or 4/5. And we knew that dw was 5. And now I'm just going to solve this for ddw. So 5 plus 12 plus 40/3 comes out to 91/3. And if I multiply both sides by the reciprocal, I get that's 3/25 times 91, or 0.31 or 0.00312. And this one was hard. What made this really hard?
The shape.
The shape of that base, right? It's just really inconvenient. But if you thought about it and broke it up in the way that we did there, not too bad. Well, still bad, but not like doable bad. Probably have time to do one more. Would you like to do one more from this section? Who's next on this? I'm going to call on Chanel unless somebody else decides they want to ask about one of these. Okay, Chanel, go ahead.
Number 24.
24, okay. Okay. This is another kind of a tough one. In particular, they don't give us a picture for this. So it says a trough is 10 feet long, and its ends have the shape of isosceles triangles that are 3 feet across at the top and a height of 1 foot. Okay, so I'm going to pause here and just take a minute to draw. Yes. Okay, so there's my trough. We're told that this is 10 feet long, 1 foot high, and 3 feet wide. Let me go back to reading here for a minute. If the trough is being filled with water at a rate of 12 cubic feet per minute, how fast is the water level rising when the water is 6 inches deep? So we're looking for the height of the water, or the rate in which the water is rising when the height of the water is 6 inches. I wrote that as just half a foot, so that all the other units were in feet. So I wanted to make sure I had unit agreement. Does this feel okay picture-wise? Yeah,
Do
Giselle.
you think on the test you would like give us a picture, or like are you like more inclined to make us draw it?
Some of both. Depends on how complicated the situation is. I think the previous one where you got a picture of the cross section would be not something I'd expect you to be able to come up with by hand or without a picture with it. This one where it's just like got a triangle on each end connected, I think is reasonable, although it's still a little challenging because you have no picture, and maybe we don't think about what a trough looks like.
Yeah, that's what I was like, what is that?
But again, all I read was isosceles triangle as the end, and just okay. Well, then it's just like like a big cup, basically. Does that feel okay?
Yeah.
Okay. So, what type of three-dimensional shape is this? It's a prism again. Yep. So I'll put a T for trough. So the volume for a prism is just area of the base times the trough. And in our case, the area of the base is what shape?
It's a rectangle.
So the base is this. It's a triangle. So 1/2. Oh boy, maybe I should have said P for prism here, because I'm also going to have a triangle also. Let's call those P's for prisms. Okay, and then 1/2 base of the triangle times height of the triangle, and then we have times height of the prism. Is everybody okay with this volume formula that we've come up with? Now let's change this to talking about water. So as we fill this with water, the height of the triangle and the base of the triangle are going to change. Everybody agree with that? So those need to remain variables. But what about the height of the figure there?
It's not gonna change.
That doesn't change. That's going to remain constant. So I'm just going to input that as 10 because that's a constant. Super critically important. You're able to identify that by like looking at the picture and thinking about the situation. Like what is changing? What is going to be remaining the same? If you miss that, it's going to be impossible to get to the correct answer. The calculus is going to get real yucky real quick because you're going to have one too many variables and nothing to get rid of it with. Are we okay so far? Now, if I look at this, if I wanted to differentiate, yes, Katie.
Why is
The base of the triangle as HW. You mean this?
no?
Right, because I want to differentiate between the height of the trough, which is 1, and the height of the water, which is a variable. It's me well, here's the thing, Katie. Like the water is also going to be the same shape as the trough, right? Because the water is just going to fill the shape of the container. But the dimensions of the water, some of them are going to be variable because there's water coming in, right? So some of those dimensions are changing with time, and some of them are not. So I always start by just like writing the volume equation of the container, and then I rewrite my volume equation for the water because it's the same shape, but here I'm accounting for what are the constants and what are the variables, right? So I want to rewrite it so that I have made it clear to myself, like, what are my variables and what are my constants? But I'm always just going to start with everything as a variable, like I'm writing a volume formula kids geometry class. Does that feel okay with what I'm trying to do? Okay. Okay. So if I try to differentiate this water equation that I've written, dV dW, we know, right? We got information about that. That base for the water, though, we don't have any information about that. Height of the water, we know what the height of the water is, and we're looking for its rate. So somehow we're going to have to figure out a way to rewrite BW as HW. Did you catch why I need to do that? You're right. Before we get there, though, did you catch why I needed to do this? Yeah, so if I tried to differentiate this, I'm going to get a dBdW or dBW dt out of that, right? I'm going to get a differential because I'm differentiating a variable, right, with respect to time. I don't know anything about this. I have no way to get that information. I can't go about differentiating that and getting stuck with a differential that I have no way of capturing. I know I need to clear that BW out before I can start doing derivatives. Is that okay? Okay. So Chanel had suggested here that we do this as a proportion. So if I look at the yellow triangle there and the black triangle, those form similar figures. So I can say that 3 over 1 equals BW over HW.
So BW is equal to 3 HW.
Mm-hmm. And now we'll substitute that in. Or 15 HW squared. Now I'm ready to differentiate. I haven't done any calculus to this point, believe it or not. It's all been algebra setup. So dVdt was 12. HW was 1/2. So 2 times 1/2 just cancel out. I divide both sides by 15. This was like feet per minute or something, I think. I'm done. I guess I could reduce that, right? I'm done. 4/5. Where's the hard part here?
Just setting it up.
Getting to piece that I'm going to differentiate. Once you've gotten to there, the calculus part is actually really easy, right? And the solving part is actually really easy. The hard part is the geometry and algebra crammed together to get the equation that you really need to differentiate. That's the hard part. If you're given the equation, though, shoot, all we do is take the derivative and plug stuff in, solve for a variable. That's all stuff we should be pretty good at this point. I think you picked the 2 worst ones from this book problems here. I think these were the 2 hardest ones. If I recall, I think these are the only 2 that require like a change of variable substitution, like building that similar triangle thing, which is the hardest part. When you have like variables that are like, oh, what do I do with this thing? I have too much stuff going on. I think the rest of them you can do without having to do that. Okay. At least from the book. The MyAP questions are not that. You have some of those that require change of variable also. All right, let's move on to something considerably easier. Let's talk about 4.1 here for a bit. Yes. Certainly. Of course. All right. So remember back in our Algebra 2, our pre-calculus classes, and we were looking to find like the maxima or minima for a function, how do we do that? We had to use our calculator. And remember when we did this, I had told you, like, at this point, you have no other method to solve this problem other than your calculator. Guess what? It's changing today. So what we're going to learn today is an algebraic method for finding those extrema, those local or global maxes and minis, for some situations. Not all situations yet. So let's start by reviewing what our definition is for like an absolute maximum and absolute minimum. And it's just like we remember. The absolute maximum is the biggest y-coordinate amongst all the y-coordinates in our function. Or a tie for first, right? And the absolute minimum is the biggest y-coordinate amongst, or the smallest y-coordinates amongst all the y-coordinates for our function, or a tie for first, smallest. But remember, a local maximum, we're looking for the biggest value. And here we use the phrase where x is near c. So what are we saying there? Is that c is on some like open interval. Okay, and that becomes important here in a minute. But the thing to remember, for these locals to exist, has to be that x value has to come from an open interval. So that's what we mean when we say near or in the neighborhood of. We're talking about an open interval. So the endpoints are not eligible to be extrema. Everybody okay with that? And the reason is, if you have like a function like this, and I say, that's my neighborhood, should there be a local max or min in there? No, right? Is there any maximum or minimum for that function? So we shouldn't have a local one in there just because we took a circle of it, right? We don't want to count the endpoints of that neighborhood as possible candidates for a local min or a max. It can only be the stuff inside of the neighborhood, not on the boundary. Does that feel okay? All right, so let's look at an example. We're just going to use our eyeballs here. So our function f of x is equal to 3x a fourth minus 16x cubed plus 18x squared on the interval from -1 to +4. Where is our absolute maximum or maxima? Right? Great. How about our absolute minimum or minima? Okay. Local max. 1 is, 4 is not, but why can't 4 be a local? Yeah, because it can't be a point inside of an open interval, right? Because there's nothing to the right of 4. That can't be a local. Everybody's okay with that? Local minima. And 3. Because that, again, is in a neighborhood, right? That's the lowest point in a neighborhood. Chanel.
Wait, so how come like that other endpoint for whatever can't be not absolute, like a local maximum again?
Locals have to come from an open interval. So tell me what interval from the domain that you can pick that contains 4 that's an open interval. I can't write one, right? Like I could do 3 to 4, but that doesn't have 4 in it, right? So that's why it can't be a local max, just like -1 can't be a local max. Does that feel okay?
Yes.
Okay. All right. Extreme value theorem. This has a pretty name. Do you think this is one that we're going to need to memorize?
Yes.
Yeah, this one should go down there with like intermediate value theorem or squeeze theorem. These will be one that will come up in the free response questions almost certainly as something that you need to quote and use by name. The extreme value theorem says if f is continuous on a closed interval, a to b, then f attains an absolute maximum value, we'll call that value f of c, and an absolute minimum value, f of d, at some numbers c and d on that closed interval. What's the piece that we have to have in order to do this? Continuous and closed interval. Okay? Those are your conditions that you need. Once you have those, you can say, okay, we know we have an absolute max and min in here. Notice that it's not local. So let's look at some examples here. If I look at this first example, I have an absolute maximum and also a local maximum. And I have an absolute minimum as well as a local minimum. This next example, I have an absolute maximum and a local maximum, and then just an absolute minimum. Not local because it's at the end point. Or if I look at this, I have 1, 2 absolute maxima, also local maxima, and 1 absolute minimum. Is everybody okay with that? Chanel?
Wait, so on picture number 2, I'm getting confused, like how do you know whether or not it's local or not? Like,
Local can't be at an end.
okay,
That's it.
is that it?
That's it.
Okay.
And it can't be at an end because of the definition that we've given it.
Okay.
That it has to be part of some open interval.
Okay.
Okay? Is everybody okay there? Now, notice that we have to have continuity for this and closed intervals. Let's look at what happens if we lose part of that definition and why it doesn't guarantee us absolute maxes and mins. Everybody okay? So let's take a look at this one. This is discontinuous, right? We see the jump discontinuity. What is the absolute maximum for this?
None.
There is not one. Notice that's an open circle. So there is not an absolute maximum here. What is the absolute minimum?
Is it 2, 0?
That does occur at 2, 0. Okay. So you could have one but not the other if we lose continuity. Let's take a look at this. Here we're continuous, right? But what don't we have? We don't have a closed interval, right?
Yeah, there's no absolute minimum. Right?
That's not an absolute minimum because it's open. That's not an absolute maximum because, again, there's an asymptote there, so it's like an open. This has no absolute max or min. Does that feel okay? Good. Okay. All right. Next up, Fermat's theorem says if f has a local maximum or minimum at c, and the derivative exists at c, then the derivative has to be 0 at c. So if our function has a local max or min at x equals c, and the derivative exists at x equals c, then the derivative at c has to be 0. We have to be careful with how we apply this theorem because it does not work as a converse. So let's look at an example of something where the derivative is 0, but we don't, and exists, but we don't have a min or a max. That example would be like x cubed. Come on. So the graph of x cubed looks like this, right? What's the derivative at this point going to be?
0.
0. Is that a maximum
No.
or a minimum?
No.
No. So there's our example, right? The derivative can be 0, but it doesn't guarantee you have a min or a max. So the converse isn't true. Let's look at a situation where we have a min or a max, but the derivative is not 0. So there's our absolute value function, right? We have a minimum right here, but what is the derivative at that point have to be? It doesn't exist, right? So if we lose that continuity piece, if we forget, or that derivative existing piece, we might miss a max or a min. Everybody's okay with that? So we have to have both parts. Okay. So this is starting to build towards our process for finding these extrema. We're going to define a new term called a critical number, and that's just the values of x where our function is either, or the function's derivative is either 0 or doesn't exist. We're going to call those critical numbers. Those will be our candidates for extrema. Everybody's okay with that idea? Or some of our candidates for extrema. Because by Fermat's theorem, if I check both of those things, I should get all the local minima out of that. So let's do an example here. We're going to find the critical numbers for f of x. So there's two things I need to check, right? I need to check where the derivative exists, and I need to check where the derivative is 0. So to check if where the derivative exists, I have to compare the domain of the derivative to the domain of our function. So let's start by figuring out the domain for f. So our function is x to the 3/5 times 4 minus x. As students in AP Calculus with your background in pre-calculus and Algebra 2, you should be able to look at this function and tell me the domain with doing no calculation at all.
All real numbers?
It is all real numbers. Great. Why? It's not, because the exponent is not, all the exponents aren't whole numbers. So this part is a polynomial. Its domain is all real numbers. What is this part?
Root function.
What kind of root? Odd root, because the denominator is an odd number, like a cube root or a fifth root or whatever. Odd roots, the domain is all real numbers also. So the domain of f is all real numbers. Is everybody good with that? That's great. Good job on your memories. Now let's compute f prime of x. What's going to be the best way to do that? You could, I wouldn't. Yeah, let's do that, right? Oops. Come on, you stupid thing. There you go. Who's confused on how I got 8/5?
Where'd you get 8/5?
Think about it for a second.
Oh, you have to add 1.
So if you add the exponents, because the bases are the same. 3/5 plus 1 is 8/5, right? Okay, now let's do the derivative of this thing. That looks way nicer to me. You agree? No product rule necessary. What's the derivative of 4x to the 3/5?
4x over 5. X. 2/5.
Is everybody okay with how we got to there? Just power rules, right? Now we're going to look at the domain of the derivative. Again, as students in AP Calculus with your backgrounds in Algebra 2 and Pre-Calculus, this should be something you should be able to look at and be able to compute the domain in your head. It is not all real numbers.
I know the second part is all real numbers.
Good. What did we lose with the first piece?
Is it, like, don't you have to set the denominator to 0? Like, equal to 0?
Great, what's the denominator?
It's x, like, that's just denominator.
5x to the 2/5?
Yeah.
When is that equal to 0? Just when x is 0. All real numbers except for 0. So what can we say immediately is one of our critical numbers?
0.
0. Is everybody okay with how we did that? I can write some more stuff out, but these are things that, like, we should be able to just kind of do in our head to some extent. Some of them might be more complicated than this, but this one is one that we should be able to look at and recognize, right? All right. Now, the other place where we can get critical values is when the derivative is equal to 0. Hi, Mr. Guest. What's up?
Sorry if we bring back one of your former runners,
Sure.
Sister Mary Margaret Payne.
Hi, Mary. How are you?
Do you know what you give none?
I didn't. I consider it none my business.
So guys, this is Sister Mary Solanas. She is a Franciscan sister and a graduate from Notre Dame Prep, class of 2015, so really not that long ago. 8 years ago.
You blink and it's gone, right?
Basically.
So she is living proof that if you go to, well, whether you go to a Catholic school or not, you guys can be a nun too. Is anybody, and you can be honest, not the guys. Everybody really ever think about a religious vocation, guys or girls?
I didn't think I was going to be in that when I was
Yeah. I don't want to embarrass you, Nolan, but anything you want to share? Like,
I don't know. Sometimes when, like, say the prayer, asking for more priests and mass, just think about it.
yeah. Yeah, at this age, nobody's expected to know for sure. Even sister joining an order has to go through vows. She was explaining every year for 5 years. And but each year you kind of remake your commitment, and then you make a decision that you're going to do it for life. Just like if you got married. You know, if you get married,
You date for a while before you pull the trigger,
yeah, yeah.
right? It's like you're dating the church for a little while before you go all in, right?
Yeah.
So what made you think about becoming a nun?
It's the same question. Like when I was growing up, people would talk about vocations and thought that'd be a possibility. I didn't want to. When I was in high school, Mr. Cool didn't think I was going to be a nun.
Didn't cross my mind.
But particularly when I was in college, just praying more and praying with the scriptures and going to mass, and I felt a deep desire to give my whole life to God. And someone had once told me that God will ask some of us to be priests and nuns, and you can say no, and that's okay. God will still love you exactly the same. But nothing on earth is going to make you happier than doing God's will. And that's exactly what I found when I really was open to religious life. And when I met sisters, I never met sisters till I started discerning being a sister, which is crazy. And I met young sisters, and the life was just joyful and beautiful, and it's true. Year after year, I didn't think I could be any happier. But doing the will of God is a profound gift.
So when I was in high school, the priests were always after me. They wanted me to become a priest, and I used to think it would be kind of cool to be a missionary, travel around the world and go help people. And then I ended up getting a girlfriend. We started dating when we were 15. We ended up getting married. So it's worked out okay doing that too. But I think that if there's one message with Sister visiting us today, keep your options open. There's a lot of people that think they're going to be happy in life if they get big jobs and big careers and make gobs of money. And that rarely brings happiness. Happiness comes from finding things that are meaningful in your life and having purpose and having a strong relationship with God. So it could be a great avenue. That's the pitch for today.
Right. Ask God what He wants you to do.
Yeah. Great point.
That's kind of good advice regardless, right?
Right.
Yeah, but everything.
Right. And so this comes up when you're thinking about colleges, when you're stressed out about schoolwork, when you're not sure.
Can't figure out your AP calculus homework.
I have to do math in the convent too, so do your math now.
Did it help? Did your education here help
Oh,
you?
yes.
Were you one of the smartest ones in the convent? Or
Um,
most well prepared?
we have really smart sisters. We have a Harvard alum. So I don't know if I'll say that.
Okay.
But
Okay.
we have a variety of different backgrounds. Musicians. I studied chemistry, so I don't do a lot of chemistry now. But
Well, thanks for letting us interrupt.
No problem.
If anybody ever has any questions and ever wants to talk to a nun, let me know and I'll let you know I get a hold of Sister Mary. All right. Thanks, guys.
no,
Bye. Thank you. Good to see you.
you taught her?
She was on I coached her for cross country. I don't know that I had Mary ever in class. All right. Let's finish this one up here. So we then have to solve this equal to 0, right? So if it's me, first order business, let's get those denominators of 5 out of there, right? That's pretty easy to see. And then I can take a 4, get that out of there. But then what? To solve this, what am I going to need to do? No. Yeah, factor. Great. What factoring can I do? Yeah, greatest common factor of x, the something. The something I would pick would be this something. That looked pretty good to you guys? So if I applied the 0 product property then and set each piece equal to 0, what's the solution to x the negative 2/5 equal to 0? No, there's no solution, right? If you have 1 over x equal to 0, that doesn't have a solution, right? Can't do anything with that. But this one does. What do we get? We get 3 over 2. So those would be my 2 critical numbers.
Mr. Bullock, I have a question. How come 1 over x equal to 0 is no solution?
What's the graph of it look like? Right? Has a vertical asymptote at x equals 0.
Oh, okay.
Right? If you can tell me what I divide by 1 to get 0, be like infinity, right?
Yeah.
There you go. Right? No solution. All right. So this leads us to statement 7. If f has a local minimum or maximum at c, then c is a critical number for f. That leads us to this procedure. Closed interval method. To find the absolute maximum and minimum values of a continuous function f on a closed interval ab. Notice continuous function and closed interval. Step 1, we find the critical values. Step 2, find the values of f at the endpoints. Plug those into f. The biggest value amongst those is your maximum. The smallest value is the minimum. Could be values, right? You could have ties for first or for biggest and smallest. All right, so let's do this example or two, and that'll finish us up for today. So this is finally getting to doing these maximum problems by hand, right? Max and min and max problems by hand. So I'm going to start finding the domain for f. What's the domain for f here? Oh, come on, guys. It's given to you right there. They told you what the domain is. In general, that's a polynomial, so the domain would be all real numbers, but that's good enough for us. What's the derivative of f?
3x squared minus 6x.
Great. What's the domain for that? Great. So really in our problem, though, yeah, still the same as the function. What's that tell us about the critical values? They're only going to be where the derivative is 0, right? That's all I have to check for is because the domains are the same. How do I solve 3x squared minus 6x equal to 0? Great. What did I factor off?
3x.
Cool. So what are my values for x then? 0 and 2. Those are critical values, or critical numbers. So what do we have to check? We have to check the endpoints, the critical number, and the critical numbers. Let's see, that's negative an eighth, minus 3/4, plus 1. That is positive 1/8, I think. 0 is just 1. That's going to be 8 minus 12. That's negative 4 plus 1 is negative 3. And that's going to be 64 minus 48. That's 16 plus 1 is 17. So what can we say here? Is that 2 negative 3 is our absolute minimum, and 417 is our absolute maximum. Right, we have to check both our critical numbers and also our endpoints. Do you want to try to do the last one here? No? If you don't, that's okay. I thought it was good trig practice. Well, we're at the end, right? Here's, look, take a deep breath. Okay. Look at the problem. This is the kind of problem you're doing, right? Is this complicated symbol pushing?
Okay.
No, the derivative is simple, right? The derivative we did there was simple. Solving for 0, or solving x equal to 0, just algebra, right? The calculus here is very, very light, mostly conceptual, to justify this process. But this process we're doing is not a difficult one, especially in comparison to like find the derivative of this like problem that has like 8 linked chain rules in it. right? That's way more to keep track of than something like this, where the derivative was something that we were effectively able to do in our head, right? Was that. You can do that now.
Let us remember how truly blessed we are for all the gifts that we have in our lives. Let us not forget. Is there no homework quiz? Also for giving no toiletries or money that is going to help those throughout our own community as well as throughout the world and our marriage mission. Dear Lord, you give each of us tremendous resources on which we can rely. You have given us courage, prudence, intelligence, and hope. Help us use these virtues to serve others and help build your kingdom. Amen. Teachers, you may dismiss your students. Have a wonderful afternoon.
Bye. Oh, the fight song. Let's go. Fire up, guys. The end of the school day.
If you want to do the IAP stuff like later, 'cause I forgot to do it.
Oh,
And
yeah, and it's
checked
locked
and
now,
it's
right?
locked, yeah.
Yeah, let me see. I have that. Where is that? Let's see. I know I needed to. Oh, is it going to be broken? Oh, no, it's okay. Let's see. I can. Let's
Yeah,
try to
like-
publish this as. See if I can get it into the OneNote here real quick. Because I told you guys I was going to do that, and then I forgot to do it. Also. How you doing in general there, Tone? Life. It's all right. Not great.
Solid.
Solid. Okay.
I'm just playing a lot of like med programs right now, so I gotta do like a ton of essays.
Oh,
so
you're
it's
just
taking up a lot of time.
you feel bogged down.
Yeah.
Yeah, I get that.
But I think second semester will be a lot nicer.
Cool. I hope I hope so, man. Right? Yeah.
Is this week and then one more weekend.
So long. Some cost. And then could I just like complete it like whenever, or like for the next homework set?
Sure. Yeah, that's okay.
Alright.
Let's see. I think.